let's do some chi-square analysis. We're first going to start off by looking at our null hypothesis and our alternative hypothesis. So remember that the null hypothesis states that there is no relationship between the variables that we are measuring. No relationship. There is nothing special happening. Nothing special going on if we are comparing things like means or rates, for example. So to use our transpiration lab as an example, we had a control rate and we had an experimental rate. Our null hypothesis for this lab would be that the control rate is equal to the experimental rate because nothing special is happening. In other words, the independent variable over here does not influence the outcome, and since it doesn't influence the outcome, there's no reason why the control and the experimental rate would be any different. For a chi-square test, the null hypothesis is that the deviations between the expected and observed are strictly due to chance. In other words, there is no statistically significant difference between our expected values and our observed values because nothing special is happening and the only thing influencing the outcome is chance. The alternative hypothesis would be something like the control rate does not equal the experimental rate, or there is a relationship, so yes to relationship. The independent variable does have a measurable effect on the treatment group or the experimental group, or for our chi-square analysis, the deviations between the expected values and the observed values are not due to chance. Okay, so by the end of our data analysis, we are going to reject one of these. We are either going to reject the null hypothesis, or we are going to fail to reject the null hypothesis, and therefore we would be rejecting the alternative. So first let me explain what I mean when I say, for a chi-square analysis, what I mean when I say observed and expected. So the observed values are simply the values that we observe from running our experiment. The expected values are the values that we expect operating under the assumption that the only thing influencing the outcome is chance. So I'll give you an example. Let's do an experiment where we flip a coin 100 times. And I'm not even going to tell you what the observed is yet. We can have a heads outcome and we can have a tails outcome. We know that the expected outcome is 50% heads and 50% tails. We're not using frequencies for our expected values. We're using frequencies to determine what number goes here and what number goes here. So in other words, if I flip a coin 100 times, how many expected heads do I get and how many expected tails do I get? Well, the probability of getting heads is 1/2, which is 50. The probability of getting a tails is 1/2 times the total, so 50. Let's change the number, and instead of 100, we'll do 124 trials. So I think I said 124. So 124 trials, so what are my expected? Well, it's not 50%, 50%. It's heads is 50% of 124, and tails is 50% of 124, which is 62, 62. Now, if you flip a coin 124 times, you're probably not going to get exactly 62 heads and exactly 62 tails because chance can cause deviations. The question that we're trying to figure out is, are the deviations large enough that they are unlikely to be due to chance? So what if I did this experiment and my observed outcome was 58 heads and 66 tails? We can use a chi-square chart to determine whether or not these deviations between observed and expected are deviations that are due to chance, or are they more likely due to something else? So the chi-square calculation is pretty simple. Once you have observed and expected, the rest is just plug and chug. It's O minus E squared divided by E. And so we do that for each category, and then we sum all of the categories together to get our chi-square sum. So for my observed, I'm going to do O minus, let's do heads, O minus E squared divided by E. And then for my tails, it's going to be O minus E squared divided by E. So if I do that for heads, I get 0.258, and for tails, I get 0.258. These numbers will not always be equal, by the way. And when I sum them together, I get a chi-square sum of 0.52. So my chi-square sum is equal to 0.52. Okay, I need two more pieces of information. I need to know what my degree of freedom is, which is simply the number of categories minus 1. So I had two categories, heads, tails, so 2 minus 1 is 1. And then the third piece of information I need is my critical value. Now you're always going to have to look up your critical value using a chi-square chart, so I'm going to go ahead and pull one up. Here is a chi-square chart. So in order to find the critical value, we're always going to be using a probability value of 0.05. This is essentially the likelihood that we make a mistake when we reject the null. And real quick, I want to clarify that when we're saying that there is a 5% likelihood that we're making a mistake, the mistake doesn't have anything to do with the fact that we're making a mistake because our data is bad, or that we did something wrong in the experiment, or we messed up somehow. What this is saying is that if we're going to reject the null, there's a 5% likelihood that the deviations really are caused by chance. They're just very, very rare, crazy deviations. That's what I mean when I say that there's always a small chance that we reject the null hypothesis by mistake. So this is our p-value, and in order to find the critical value, we're just going to line up the p-value with the degree of freedom, and in this case the critical value is 3.84. So our critical value is 3.84, and the rule is that if the chi-square sum is greater than or equal to the critical value, then we reject the null. And when we reject the null, we're doing so with at least 95% confidence that we are not rejecting it by mistake. If the critical value is less, let me say that again. If the chi-square sum is less than the critical value, then we fail to reject the null. In other words, it is likely, if we fail to reject the null, what we're saying is that it is likely that the deviations are due to chance. And if you remember, I think my deviations were, instead of 62, 62, I had something like, what, 58 and 64? So what I would conclude is that these deviations from my expected were not large enough to allow me to reject the null. So I fail to reject the null. 0.52 is less than my critical value, which is 3.84 or 3.86. No, it's 3.84. Okay, so let me show you another example really quick. So we have 124 flips. Let's say instead of 58 and 66, I got something like 50 and 74. Here my chi-square sum ends up as 4.65. So let's go down here, 4.65. When our observed is 50 and 74, those are pretty large deviations compared to the expected 62, 62. And what we're saying is that the deviations are so large that we can reject the null hypothesis and state that the deviations are likely not due to chance. Now, in this case, we'd actually be wrong. And we know, or I know that we're wrong because this coin flipping simulation is fair. It just so happens that we, by crazy, crazy chance, got very large deviations. But remember, whenever we reject the null, it is possible that we reject it by mistake. That's what that probability value of 0.05 means. It means that, look, when you reject the null, there's always a chance, approximately 5%, that you're going to reject it by mistake, because it is possible sometimes to get crazy, crazy large deviations. What we're saying here is that if the deviations are crazy large enough, then we can state with at least 95% certainty that they are likely due to something other than chance.